Having seen a few different methods that use various aspects of a CNN model to explain its predictions, such as its activations at different layers, its gradients, its output probabilities, so on and so forth, we'll now look at what are known as class discriminative saliency maps or class discriminative attribution maps. By saliency maps, we mean maps or regions in an image that are salient for a given prediction. And by class discriminative saliency map, we mean a saliency map that helps distinguish one class from another. For example, if we had a cat and a dog in an image, which part of the image led to it being predicted to be a cat, and which part of the same image led to it being predicted as a dog. Let's see this in more detail over the next few slides. So the question we still continue to ask is, can we know what a network was looking at while predicting a class? But the approach, as you will see, is different from what we've seen so far. One of the earliest methods in this regard was known as class activation maps or CAM, which was published in 2015 and 16. So this takes a convolutional neural network and uses the notion of global average pooling to achieve the objective. So let's look at this in more detail. So if you had, say, 5 to 6 convolutional layers in your architecture, you take the last convolutional layer, and then for each map in that convolutional layer, remember you could have 100 filters, you would have 100 maps. So for each of those maps, you do global average pooling or gap. What does global average pooling do? You take a particular attribution map or a feature map, not an attribution map, a feature map, this green one, and you average all the intensity values there into one single scalar, and that becomes this green circle here. Similarly, you take the red feature map and average all its values, and it becomes the red scalar here. You take the blue feature map, average all its values, and it becomes the blue scalar here. It's global average. It takes the average of the entire image. Now, what do we do with these global averages? Having these global averages, so each of these scalars here represents one feature map. Now, we learn a simple regression model or a linear model that takes us from these scalars to each of the class labels on the last layer. So for each of the class labels in the last layer, we learn a W1 into the first attribution, into the first feature maps average, plus W2 into the second feature maps average, and so on and so forth until Wn, where n is the number of feature maps in that last convolutional layer. Now, how does this help us? So for a given image, such as the image that you see here, if you forward propagated this through a trained AlexNet, you would get a set of n activation maps as at the last convolutional layer. Let's assume that these are those activation maps. So you see one here, the second one here, and so on and so forth until the last one here. Now, the weights that we learned between the output of the gap layer and the classification layer are now used to weight each of these activation maps, and when you do a weighted sum of all of these activation maps, that gives us the contribution of these activation maps towards one particular class label. In this example, let's say we want to predict this image as belonging to an Australian Terrier, then you learn weights corresponding to each of those activation maps to the Australian Terrier class, and you weight each activation map in the same way, and this weighted combination of activation maps of that conv5 layer corresponds to the Australian Terrier. If you say wanted to predict a man in the image through this, then you would have a different set of weights. Maybe let's say this was the man class. So then you would have a different set of weights of the same activation maps that connect you to the man class So a different weighted combination of the same activation maps will tell you which part of the image corresponded to the man class. Now this approach gives us a way of getting us class discriminative saliency maps. There are some advantages and disadvantages, as we will see soon, but here are some visual examples to start. So you can see here that in the first 3 images, it is examples of the class Briard, and the second 3 examples, it's the class Barbells. And you can see here that in each of these cases, the CNN model looks at this particular region and calls it a Briard. Similarly so in this case, similarly so in this case, and similarly for the Barbells, you can actually see that the CNN looks at the weight plates to make the decision that this image corresponds to Barbells. So obviously you can ask the question, what if I changed the class? So let's see an example for that too. So here is an image, and here are the predicted saliency maps or class activation maps for the top 5 predicted classes based on this image. The top 5 predicted classes were palace, dome, church, altar and monastery. And you see here that when the model was predicting palace, it was looking at the entire structure. When it was predicting dome, it was only looking at the dome. When it was predicting church, it looked at only the facade close to the dome. And similarly for altar and for monastery, it was looking at certain parts which probably made it think it was a monastery. So this gives us, as we just mentioned, class-specific activation maps which can be useful in practice. An intuition for doing CAM is that in any CNN so far that we've seen, in most CNNs, we've had a few convolutional layers, then followed by some fully connected layers. Convolutional layers do maintain a certain level of object localization capability. If you recall, in the first lecture, we saw an example of the conf5 feature map with 2 people sitting in an image. And we saw that the feature map actually showed where they were positioned in the image. So the convolutional layer did give us an idea of where the objects were localized with no supervision or with no details given to us explicitly. However, if you try to look at the representation that you get after a fully connected layer, for example, the FC7 representation, you would lose this information. That's the very nature of the difference between a convolutional layer and a fully connected layer. So that's one of the reasons for developing a convolutional layer itself. So that is now, by doing the CAM based approach, we actually see now that we can retrieve back the activation maps of the 5th layer and be able to use them to explain our decisions at the classification layer. These are just more examples here of the localization capability of CNNs in different feature maps. And you can see here that you have different receptive fields of convolutional units and the patches that maximally activate that patch. And you can see here that you do get a certain you get a certain sense of localization through these kinds of feature maps at different convolutional layers. You obviously lose that when you go to fully connected layers. Here are a comparison of CAM maps across different models. You can see here, this is applying CAM or using GAP, Global Average Pooling, on GoogleNet, VGG, AlexNet, just GoogleNet alone, another architecture known as NIN or Network in Network. And these are compared with a backpropagation on AlexNet and a backpropagation on GoogleNet. Backpropagation is your data gradient. Remember, we talked about the data gradient in the earlier lecture. So this is that visualization. And you can clearly see that CAM gives a far stronger saliency map, a far more useful saliency map when compared to the data gradient. What are the pros and cons of CAM? Can you think about it? Can you think of any significant disadvantage of CAM? Advantages: class discriminative, can localize objects without any positional supervision, and it does not require a backward pass through the entire model, unlike something like guided backprop or backprop to image. What are the disadvantages? The disadvantages, the key one is that the key one is actually the third bullet here, which is there is a need to retrain these models to be able to get those weights that we get after global average pooling. After training in AlexNet, you still have to do global average pooling and learn those many linear models at the last layer to be able to understand the relationship between the activation maps and each class label. You will have to do this retraining explicitly for explanations on top of training your AlexNet or any other CNN model, and that can become an additional computational burden. And we are imposing a constraint on architecture by saying that you will have to introduce a global average pooling layer to be able to explain your model, and that may cause problems when you want to generalize to many vision tasks using this kind of a method. And there is a chance that the model may trade off accuracy for interpretability. So to get a better interpretability, it may end up achieving lower accuracy if you used the gap model and the corresponding weights itself for classification. Now let's try to see how we can address these disadvantages, which was done in a follow-up method called Grad-CAM, which is published in ICCV of 2017. ICCV is a top-tier computer vision conference. Grad-CAM stands for Gradient Weighted CAM. As we will see in the next few slides, it's a very intelligent approach on repurposing CAM using existing quantities in a CNN, and let's see how that works. But here is the overall idea and architecture. We will describe each of these components over the next few slides. So you have the input image here, you send it through a CNN, you have your convolutional feature maps, and the convolutional feature maps could be followed by any task specific network. You could be doing classification, which is what we have seen so far, but you could also use their approach for any other tasks such as image captioning or visual question and answering. These are tasks that we will see later in this course. Irrespective of the task, we assume now that there is a last layer, there is a loss, and there is a gradient, which can be assumed in any neural network for that matter. Once you have the gradient of a loss with respect to any task, you have now gradients with respect to all of the feature maps or the activation maps. You now combine them, you combine the gradients that you get for each of those activation maps, and they automatically become your weights for each of the feature maps. And in Grad-CAM, because we want to ensure that only positive correlations are shown in the final saliency map, we apply a ReLU on the weighted combination of the activation maps, and that becomes our final Grad-CAM saliency map. The method also talks about adding guided backpropagation to make a variant of Grad-CAM called guided Grad-CAM. Let's see this in a bit more detail and also mathematically as to why Grad-CAM becomes an extension of CAM. From CAM, mathematically speaking, we have YC, which is your scores or the class scores in the last layer, which is given by summation over K, which is all your K feature maps. We assume now that you have K such feature maps, and you have the class weights for each of these feature maps, and summation over I, summation over J, AI, JK, 1 by Z is going to be your global average pooling of each of the K feature maps. And then you have the weights, and in CAM we know that these WCKs, WC corresponds to the weight for each class and WK corresponds to the weight for each activation map. So you need to do both. This is what we learn through linear models in that last layer. Now let's go from there. Let's now assume that F superscript K is given by the last terms 1 by Z summation over I, summation over J, Aij superscript K. then you're going to have yc is going to be given by, sorry, there is an equal to missing there. So you're going to have yc to be equal to summation over k wck into fk. We're simply replacing the last terms with fk. And if you now took the gradient of yc with respect to fk, you have dou yc by dou fk is equal to dou yc with respect to dou aijk divided by dou fk with respect to dou aijk. We just have the same component that we are taking the derivative with respect to. If you look at this closely, dou yc by dou fk, which is what wc is, we can see that from this equation here. Remember once again that this yc is equal to summation wck fk. So which means dou yc by dou fk will be wck for a particular k, whichever fk you chose for a particular feature map. And that is given by dou yc with respect to dou aijk divided by dou fk by dou aijk. Now dou fk by dou aijk, by the very definition of fj, will turn out to be 1 by z. And because that's 1 by z in the denominator, you get an into z on the numerator here when you write this out more clearly. So what does this tell us? Now if we sum the terms on the left hand side over I and j, which are all your pixel locations in each feature map, you similarly have a summation on the right hand side. Now the summation over I and j for wck, because wck does not depend on I and j, is just going to be z, which is the total number of pixels in each feature map or activation map. And similarly the z constant comes out here and you have your summation over I, summation over j, dou yc by dou aijk here. Rather, we can say wck then is given by summation over I, summation over j, dou yc by dou aijk. This tells us something important, that the wck, which we actually learned in the CAM model, are actually simply the summation of the gradients of each of the class core with respect to every pixel in the feature map and adding them all up. So in truth, the classed feature weights here are the gradients themselves, and we actually don't need to do the retraining the way we saw it with CAM. You don't need the global average pooling, you don't need the retraining. Those weights that you did the global average pooling for can actually be obtained as gradients of the last layer scores with respect to any feature map or activation map with which you want to compute your saliency maps. So which means we can now write out wck as summation over I, summation over j, dou yc by dou aijk. We're going to have a normalization factor 1 by z because we want to divide it across all of the pixels. This becomes our new weight, and our final saliency map or the localization map in Grad-CAM becomes given by summation over k, wck ak, where ak are the different k activation maps that we have. And because we want only the positive correlations to be shown on the final saliency map, we apply a ReLU on it to get the final image. You see examples now. For an original image, here is the Grad-CAM for cat, which focuses on the cat, and similarly doing this with a ResNet model, here is the location of the cat, and similarly for a dog, it looks at the dog to be able to say it's a dog, and similarly for the ResNet model looks at the entire dog to be able to say it's a dog, which is quite good. But one careful observation here is that the network actually predicts this to be a tiger cat and not just a cat. So can we elaborate on this further and see why it's a tiger cat and not just a cat? Can we try to do anything further? And here is where the method now proposes a variant of Grad-CAM called guided Grad-CAM, which brings together guided backpropagation that we saw in the earlier lecture and Grad-CAM together and juxtaposing them one on top of the other by doing what is known as a Hadamard product or a pixel-wise product. And we now see that taking this particular region, which was pointed out by Grad-CAM, and combining it with guided backpropagation's output in terms of what was salient in the image, we now get a clearer estimate of what was the dog. Remember, guided backpropagation was not necessarily class discriminative. So if you only used that, you would also have other kinds of pixels which are active, as you can see here. But by combining it with Grad-CAM, we get a more localized understanding of what the CNN was looking at while calling it a dog. And now you see why you called it a tiger cat, why the model called it a tiger cat, because you take the Grad-CAM saliency map and combine it with guided backprops output again, and you actually get this kind of a output which shows the striations on the body of the cat, which explains why it was a tiger cat. Grad-CAM went on to also show how this method could be used for what are known as counterfactual explanations. Rather, can you try to find out which class or which region in the image maximally affected my model in calling an image as belonging to a dog? So I have an image, I want to label it as a dog, and the model does give me certain probability of the label being a dog. But can I find out which other pixels in the image may have suppressed my probability for a dog as the output of the model? And this can be done by using the exact same Grad-CAM procedure. The only difference now is use negative gradients instead of the positive gradients, and this would tell us which combination of feature maps or which weighted combination of feature maps were negatively influenced a particular class probability to be high, and that would give us what are known as counterfactual explanations. And eventually, how do you use this? You can remove or suppress these features in some way to improve the confidence of the model if you would like to use it in that particular way. Grad-CAM, however, had some limitations when there were multiple instances of objects or when there were occlusions in the image. So here is an image where there are multiple dogs, and you can see that Grad-CAM gives such an output where it doesn't seem to capture all the dogs in the image. Maybe it does somewhat well when there are a fewer number of objects. There are still 3 dogs here, and Grad-CAM captures 2 dogs but misses the one in the middle. That's one of the limitations of Grad-CAM. Another case where it seems to not completely get a good saliency map is where there are occlusions. You see a bird here whose legs are hidden underneath the water, and as well it has a beak, and here you see a hedgehog which has a beak-like structure too. In both of these cases, Grad-CAM doesn't seem to capture those aspects which are actually salient aspects of that object as class discriminative in its visualization. Can we do something about it or are there any limitations in the formulation of Grad-CAM itself that we can improve? And this was done in a work called Grad-CAM++. And the main motivation of Grad-CAM++ is observing that Grad-CAM took the gradients of dou yc with respect to each of the pixels in your activation maps, and then took an average of all of them to get its final weight. In a sense, it's weighting each pixel equally by taking the average when it gets the final weight. Grad-CAM++'s idea states that maybe pixels that contribute more towards a class should get more weight than have equal distribution while computing this weight WKC. Let's see how we can do that. So this can especially suppress activation maps with lesser spatial footprint. Rather, we saw this example on the previous slide too. When you have 3 dogs and there is one dog which is smaller, the other 2 dogs got most of the gradient and the third dog did not, because it has a lesser spatial footprint. We'll see this more clearly on the next slide. And when you have this kind of a bias in the visualization, some of the smaller objects may just not be picked up in the saliency maps. What can we do about this? Grad-CAM++ suggests that we retain the same formulation of Grad-CAM. However, this time, while computing your final weight WKC, we are going to give each pixel in each activation map a certain weight as to how they must contribute to that saliency map. So let's call those constants alpha sub ij superscript kc. So alpha sub ij corresponds to each ijth location of a feature map, k corresponds to the kth feature map, and c corresponds to the class which we want to maximize. Grad-CAM++ also adds a ReLU here to ensure that only positive gradients are considered in the computation of this weight. But the larger question here is, how do you get these weights? In Grad-CAM, it was simpler to average all of these gradients that you get and use that to get a WKC. And remember, each WKC then becomes the weight of the kth feature map towards the cth class. So, but now how do you compute these alpha ij's at each pixel level? Before we go there, let's try to understand the intuition of Grad-CAM++ again visually. So here you notice that if you had an image with three different objects, say dogs, a dog occupying a larger spatial footprint, another dog occupying a mid-level spatial footprint, and another dog occupying a small footprint. And for the moment, let's assume that different feature maps capture different dogs. This, for instance, could be any other object for that matter. Could have been a dog, cat, and a jug or something like that. So each feature map, let's assume, captures each of these objects. And you see here that in Grad-CAM, when the saliency map gradients are computed, you can see that the area with the largest footprint ends up getting most of the gradient, while the gradient towards the rest of the pixels are smaller because they have fewer pixels and hence contribute lesser towards the output. While Grad-CAM++ tries to overcome this by doing the pixel-wise weighting, and you can see here that in Grad-CAM++ the weights are in the same range, the gradients are in the same range when you use this kind of an approach. This is actually the final saliency map that's in the same range for Grad-CAM++. So we still are left with the question in Grad-CAM++ as to how do you compute those alphas at a pixel level. We are not going to derive this here. This can be lengthy and that's going to be part of your homework. But what happens is, by reorganizing the gradients and using some arithmetic around the expressions of the gradients, Grad-CAM++ shows that alpha sub ijkc can actually be obtained as a closed form expression of several gradients that you have already with you. Both AB and ij here are iterators on the same activation map, and you can go ahead and look at the paper for Grad-CAM++ to understand how this derivation is done. But once this derivation is done, the rest of it stays very similar to Grad-CAM. In Grad-CAM++, you still do a ReLU at the end of summation over k, wck ak, where wck is given by summation over I, summation over j, alpha ijkc, ReLU of dou yc by dou aijk. How does this help? You now see that given the same image of multiple dogs, while Grad-CAM did not localize all of them effectively, Grad-CAM++ seems to get a better saliency map around the dogs, and it works a bit better even when there are three dogs, and it also captures the setting when there are structures such as beak or legs under occlusion as when compared to Grad-CAM. Grad-CAM++ also showed that the saliency maps obtained from Grad-CAM++ give better localization if compared to the bounding boxes that are provided with images when compared to Grad-CAM, and you see several results here. The first column in this left block are the original images. Then you have the corresponding Grad-CAM visualizations for each of these classes: hare, American lobster, grey whale, and a necklace. And you see the Grad-CAM++ localization, which seems to be better, especially for some things like grey whale when compared to Grad-CAM. You see a similar set of images for another grey whale here, a kite, a go-kart, and an eel, where Grad-CAM++ localizations improve over Grad-CAM by considering the pixel-wise weighting strategy. Here are more examples of Grad-CAM++ for multiple occurrences of objects. Once again, improved performance over Grad-CAM. For homework, there are these 3 papers, CAM, Grad-CAM and Grad-CAM++, and your job would be to read through them. And the other exercise would be to work out how we get the closed form expression for alphas in Grad-CAM++. References.